Hey guys, how's it going? Welcome to an introduction to game theory. Now, before we get into it, I want to give you a quick definition of what we mean by game theory. Okay, so game theory is the study of strategic decision making in a multiplayer game. Let me go ahead and break down each of these words and key phrases for you. So, what do we mean by strategic? Well, we mean that each player playing the game will try to maximize his or her payoff. So, payoff is key in strategic. Okay, and what do we mean by decision making? Well, that sort of implies that each player will have a choice between his or her options that he can choose from. And we call these choices in game theory his set of actions. Not a too uncommon word, but very important. Alright, now I'm sure you've heard about multiplayer games. I mean, there are plenty of multiplayer games out there. All we mean by this is that we primarily look at games where there are a minimum of 2 players. So 2 or more players. Today we're going to be considering a very popular game, 2-player game. And yeah, it should be good. And this means that in game theory, we sort of have another dimension of decision making, because not only do your decisions affect your payoff directly, but also the decisions of other players around you affect your payoff or your gain. I should say that payoff is sort of the game theory equivalent of gain. What we mean by a gain or a profit or anything like that. Okay, so what are the outcomes in any game theory game? Well, the outcomes are determined by not only the action that you pick and you are playing, but also the actions that other players play. So we're going to talk more about outcomes and show you exactly what I mean by them later on in the video, but I wanted to give you a quick sort of introduction to that. Okay, so the first game, or the only game, I was going to include more games, but I thought it may run a bit late. So the only game we're going to deal with today is called The Prisoner's Dilemma. Now, this is a 2-player game, and there are 2 players in it. Let's say 1 man and 1 woman. And they are both criminals. They've both been convicted of a minor crime, but now they're also suspected of committing a major crime together. And they're currently both in questioning in 2 separate rooms with 2 separate police officers. So, what are their actions in this game? Well, they can either 1. Confess to committing the crime, or number 2, keep quiet about committing a crime. Keep quiet. I'm just going to write quiet. And both players have both of these 2 options. And these are the only 2 actions they can choose. So, for it to be a game theory sort of game, we have to establish 2 conditions which are pretty important. First of all, both player has no idea what the other player will decide to play. What we do know is, for example, if we're player 1 and we know we have these 2 options and the other criminal 2, has the same 2 options, but we have no idea which option she is going to pick. So we have a sense of uncertainty, which is a key concept in game theory. We're not sure what the other players are going to play, so we have to take that into account. Also, what we do know is we know our payoffs or our gains in each of the in each outcome of the game. So we know aware of our payoffs. And why is this important? Well, this will give us the ability to solve such a game from either perspective. Okay, so I think I've covered, and each player is going to try to maximize his or her payoff. So they're pretty selfish, and that is a theory in most game theory problems. People are selfish, they care about their own payoff primarily, and actually only, not even primarily. Okay, so let's go on to what I've constructed here. Let me go ahead and cover that up right there. And this is what we call a payoff matrix, which represents our prisoner's dilemma game. So you may not have seen this before, but it isn't too complicated. It's sort of like a table, and it displays each of the 4 outcomes which are possible in this game. And as you can tell, we know we have these 2 strategies, and we know the other player has these 2 strategies, and we are aware of all of our payoffs in each situation. And these payoffs represented are not only our payoff or player 1's payoffs, but also player 2's payoff. Okay, so before we get into solving such a game, let me just explain what these payoffs represent. So, for example, if both players confess, we will get it let off a little bit easier, a little bit lighter, and we will both receive 3 years in prison. I've written a negative sign for a payoff because, I mean, time in jail is a negative payoff. We don't really want it. So, yeah. Okay, so -3 represents 3 years in prison for both of us here. However, if player 1 confesses to the crime and player 2 keeps quiet, player 1 will get a huge advantage. He'll be able to walk out of here a free man. Player 2 will get 10 years in prison for keeping quiet, for like sort of not admitting to it. And in the same way, if player 1 keeps quiet and player 2 confesses, he will receive 10 years in prison and player 2 will receive 0. He can walk out of here a free man. And if they both keep quiet, this is where it gets interesting. They both receive a payoff of -1, which is 1 year in prison. Alright, so how do we go about solving such a game? What we have to do is consider what we call the best response of each player. And what that is essentially, because we don't know what the other player is going to play, we need to come up with a strategy which is all-encompassing. So no matter what the other player plays, we're sure what we want to play, basically. Okay, so how do we do that here? Let's pretend we're player 1. And we're going to assume that player 2, because we don't know which strategy he's going to pick, we have to think about them independently. So let's assume player 2 is going to confess. We want to maximize our payoff, so we would like to confess as well, because -3 is superior to -10. So I'm going to circle this, and it represents that our best response to player 2 confessing is to confess ourselves. In the same way, if player 2 keeps quiet, we will want to get the payoff of 0, so we will want to confess again, and that is our best response to player 2 keeping quiet. In the same way, if we're player 2 and we need to consider the best responses to player 1's actions, let's cover up quiet and assume player 1 is going to confess. Then we want to confess as well, because -3 is superior to -10. And now considering the bottom row, we have the ability, so if player 1 is going to keep quiet, what do we want to do? We want to confess because 0 is better than -1. So here we have the best responses. Now, where is the solution to this game? It is precisely where the best responses coincide, which is only at one location in the 4 outcomes here. So we have a solution right here, where both players confess and they both receive 3 years in prison. Now you may be thinking, hey, this is kind of a silly methodology because isn't -1 far superior to this? It is more optimal, and surely you could convince them both to keep quiet, right? Now that's where you're wrong. Convincing them to keep quiet is kind of hard because the players here are maximizing their own payoff. So there isn't a concept of loyalty or trying to create an optimal ground for both players. Okay, so what we have to do to show that this is a stable equilibrium and this is a not so stable equilibrium, so not a solution, is we have to define what it means to be a Nash equilibrium. Alright, so here we have the definition of a Nash equilibrium. It is a set of strategies for all players in a game such that no player can profitably deviate. So no player has profitable deviation if the strategies of the other players remain unchanged. There's a very important concept in all game theory courses, and it isn't too difficult. So in order to explain it a bit better, let's go back to our prisoner's dilemma example and check why this is a Nash equilibrium. Okay, so if you remember, the key idea is that each player has no incentive to deviate. And what do we mean by deviate? Well, if both players are playing confess, player 1 could say, hey, wait a second, what would happen if I switched over to quiet? To keep quiet. However, that would not be a good idea because -10 is not as good as -3. So player 1 doesn't have any incentive to deviate in this position. Player 2 could be like, hey, wait a minute, what if I switch to keep quiet while player 1 is still playing confess? But nope, that doesn't really work out because I get a payoff from -10, which is 10 years in prison, which is far more than 3 years in prison. So I don't want to deviate either. So for this reason, confess is a Nash equilibrium. Now let's explain why -1, where both players keep quiet, is not a Nash equilibrium, unfortunately. So if, let's assume, both player 1 and player 2 are keeping quiet, like maybe beforehand they were like, hey, let's both keep quiet in the interview today. Now player 1 could go behind player 2's back and in the room because player 2 has no idea what player 1 is going to say. So maybe they agreed to keep quiet together. But then player 1 is like, hey, wait a second. If I confess to the crime and I know player 2 is going to keep quiet, I can up my payoff to 0. I can improve my payoff by deviating, which is huge because then player 1 would always switch to confess, and this would be the outcome because player 1 has no care in the world for what player 2's payoff is. He just wants to improve his own and get off free. So he would deviate, and in the same way, if player 2, if they were both playing quiet, player 2 would also want to deviate because player 2 is like, hey, wait a second, if I know player 1 is going to keep quiet, then I can deviate to confess and receive a payoff of 0, which is superior to -1. So I have profitable deviation too. And because both players have profitable deviation, this cannot possibly be a Nash equilibrium, and it cannot be a sustainable equilibrium. However, in the future, if you continue to look at game theory and learn more about it, you will learn about some sort of punishment strategies which will allow you to make a Nash equilibrium where there otherwise wasn't, to make more optimal allocation for everyone. And that's kind of a teaser. I wanted to add that in there because I wanted to show you how game theory is not just about, selfishness. There is a way to encourage a more optimal allocation, but not right now. So guys, I hope you enjoyed this video. I really enjoyed talking about it, and hopefully you have a good sort of beginning understanding of game theory. Anyway guys, later.